Welcome to The Explainer. Today, we're diving into the state of quantum computing in 2025, a year the UN has actually named the International Year of Quantum Science. Why? Because the game is changing. This incredible technology is finally starting to move out of the lab and into the real world, and that marks a huge turning point for all of us. So here's our game plan. We'll start with why 2025 is the start of what experts are calling the middle game. Then we'll look at the high-stakes race to build the hardware. After that, we'll explore the two sides of the quantum coin, its unbelievable world-changing promise, and the serious threat it poses to, well, everything digital. From there, we'll see how the world is trying to defend itself, and we'll wrap up with the biggest question of all. Just how close is this new reality? All right, let's jump right in. For years, quantum computing has felt, well, pretty theoretical, right? Kind of stuck in this noisy experimental phase. But we're seeing a major shift. We are now entering an era where these machines are moving beyond just theory and are starting to show some real, tangible utility. And this is where that middle game idea comes from. It's a perfect analogy, really. Think of a chess match. We're past the opening moves of pure research. Now we're in the thick of it, that complex, strategic part of the game, where the winning approaches are going to start to pull ahead, and others, well, they'll fade away. It's where the winners and losers will really start to emerge. So who's actually building these incredible machines? It turns out the race to build a useful quantum computer isn't being fought on a single front. It's more like a multi-front campaign, and believe me, there is no single guaranteed path to victory. And you can see just how different the bets are. You've got superconducting qubits. That's the path IBM and Google are on. They're super fast, but you have to keep them colder than deep space. Then there are trapped ion systems, which are amazingly stable. Their info lasts for a really long time, but they're a pain to scale up. And then you have these newer approaches like photonics and neutral atoms, which have a massive advantage. They can work at room temperature. Everyone is betting on something different, trading off speed for stability or stability for scale. And this really highlights the two dominant philosophies from the big tech giants. IBM is playing what they call a utility-first game. They want to get value to customers now by plugging quantum processors into the supercomputers we already have. Google, on the other hand, is on a quest for the Holy Grail, a massive, perfectly error-corrected machine by 2029. That's a computer that can literally fix its own mistakes as it goes. Two very different strategies. Okay, so with all this money and brain power being thrown at the problem, what's the actual prize? Let's talk about the incredible upside, because the potential applications here are, well, they're truly mind-bending. In medicine and materials science, quantum computers could be absolute game changers. And the reason is simple, actually. The world at a molecular level is governed by quantum mechanics. So to simulate it perfectly, you need a quantum machine. Companies like Pascal are already using this to do things like analyze proteins, which could slash the years and billions of dollars it takes to discover new life-saving drugs. And this isn't just for scientists in lab coats. Think about the hardest optimization problems in the business world. For finance, JP Chase is looking at quantum to build better investment portfolios. For AI, it could supercharge how we train complex models. And for logistics, it could finally crack those nightmarish routing problems for companies like Amazon or FedEx, saving them billions. But, and this is a huge but, with all of that incredible promise comes an equally powerful danger. And this is a threat that affects every single one of us, our data, our privacy, our national security, everything. The threat has a really chilling name: harvest now, decrypt later. And here's how it works. Right now, adversaries are stealing and stockpiling enormous amounts of encrypted data. They can't read it yet, but the plan is just to sit on it and wait. Wait for a quantum computer powerful enough to exist, and then they can unlock it all. It means that data you think is safe and secure today is already vulnerable. The master key to this threat is a quantum algorithm that was actually figured out way back in 1994, called Shor's algorithm. It was designed to do one thing, but do it incredibly well: find the prime factors of gigantic numbers. And unfortunately for us, that one little math trick happens to be the foundation of almost all the encryption that protects our banks, our communications, even our government secrets. So, what would it take to actually run Shor's algorithm on a meaningful scale? Well, researchers have done the math, and the number is staggering. To crack a standard encryption key in, say, 8 hours, you'd need a machine with about 20 million stable qubits. Now, to be clear, we're not even close to that today, but that's the number everyone is racing towards, and also the number we're racing to defend against. So, faced with that kind of threat on the horizon, what do we do? Well, there's a massive global effort underway to build our defenses before that 20 million qubit machine ever arrives. The world's defensive strategy is called post-quantum cryptography, or PQC. The basic idea is to create a whole new generation of encryption, new digital locks, basically, built on different kinds of math problems. Problems that we're pretty sure are hard for any kind of computer to solve, whether it's classical or quantum. And this whole effort is being led by the US National Institute of Standards and Technology, or NIST. And this isn't just theory, by the way. This transition is happening right now. NIST published the first official PQC standards back in 2024. Now, in 2025, US federal agencies are being pushed to require this new crypto in their contracts. The timeline is set, and by the early 2030s, it's going to be mandatory for all national security systems. The migration is on. Okay, so this all leads us back to the big, multi-trillion-dollar question: when? When will a quantum computer powerful enough to break our current encryption actually get here? And the honest answer is nobody knows for sure. When you ask the experts, you get a huge range of predictions. The optimists point to as early as 2030. The majority view seems to cluster around 2035. And then the more conservative folks push it out to 2039 or maybe even later. That decade-long gap in predictions, that's what makes this whole problem so incredibly difficult. And that uncertainty creates this massive strategic headache, sometimes called the quantum paradox. It forces this really difficult choice on governments and big companies. Do you spend enormous amounts of time and money upgrading your security right now for a threat that might still be a decade away? Or do you wait for a clearer signal and risk that by the time you see it, it's already way too late? And that's exactly where we are today. The quantum middle game has begun. We've got this incredible promise to revolutionize science and industry on one side of the board, and the existential risk of a global security crisis on the other. And remembering that adversaries are already harvesting our data today, the real question becomes the one right there on your screen. Is waiting for certainty really a risk any of us can afford to take?